Good evening, everybody. So here is our 994th monthly meeting, countdown to 1,000. So who can help me with the, I don't want to switch off the entire light. Somebody can take care of the lighting? Appreciate it. Thank you. Thanks a lot. So today we have the speaker, John Swoboda. He's a research scientist from MIT Haystack, with whom we have a close relationship with too. Our clubhouse is there near their observatory and so forth. So jumping into the next agenda. So as you remember, the last couple of times we had an agenda where the speaker was coming in first, but John specifically wanted this. He wanted a little bit more time. He was quite busy with things, so he wants another 45 minutes before he can start the talk. So we decided to accommodate it. So there is no voting today. So otherwise, I would have asked for you to vote on it. So here, the president's message. So what do I have to tell you about today? So, yeah, I was at the winter star party. It was great. I bought out 3-4. So for 3 or 4 days there, met Mario and Diana. They were all giving talks. Mario was talking about fixed insight and workflows related to it, and Diana was talking about her career in astrophysics, and now she's editor-in-chief of Sky and Telescope. So that was exciting. So the next month, I don't know how many people are going to the NEAF. So I hope to see many of you there who wants to spend a lot of money buying the next set of equipment. Yeah, So I also want to mention that Rich Nugent has been working on assembling the slate of candidates for the nominating committee election at our April meeting. So if you know anyone else who is interested in serving, please let us know and we'll add them to the list, and members will then vote at the main meeting.
All right, let's get right into this, all right? Recently we had an eclipse of the moon, right? I don't know how many got out to actually look at it, right? It was an early morning event, lovely. So I've got some slides from members, and I'm just gonna pop through them really fast in the interest of time. This is a nice shot by Joseph Rothschild with his C-Star S30 telescope. Lovely shot of the partial phase of the moon. For those that didn't see it, this was an early morning, pre-dawn sort of event when the umbral phase began here in the Boston area. The moon was only about 15 degrees above the western horizon and setting fast. So what you really needed for this was a superb unobstructed view to the western horizon. Not many of us enjoy such things. There's a great shot by Doug Paul. Next slide. Naz, love it. Mark Helton. Mike. I won't try and destroy your name. Mike S. Mario sent this picture of the moon. I don't know what to make of that. It must have been a really dark eclipse. The next slide, that's me. It was funny when I was previewing the slides, looking through there, Mario's came up empty. I was like, wait, what? So I had to go dig it back out of emails and stick it back in there. But that was Mario shot at totality. And I think this is a junky shot that I took as the moon was sinking behind some trees. I intentionally overexposed to get a little bit of that orange color. And I think that's it. Now, Al has a nice totality slide that's in the newsletter, right? You can check that out there.
Yeah, and it is totality, 6:05
yep.
in the morning. So
really loving this guy. Really, and I like the pink color.
It was 2 degrees above the clouds.
2. Fantastic. Well, while we're out looking up, right, we might as well get out there and look at some planets. And so Venus is now pulling away from the sun in the evening sky. Has anybody gone out to look at it, at least take a peek at it? Just driving along, eyes off the road.
During the planet alignment.
Right, we're all 9 planets aligned.
No observing while driving. It's at minus 3.9 magnitude, 10.2 arc second apparent diameter, 96% illuminated. Remember, it's on the far side of the sun. So when we look at Venus now with a telescope, it's tiny. The apparent disk is small because it's far away, but it's also nearly fully illuminated. And it's sort of rare to see Venus like that, right? We normally look at Venus when it's a nice thin crescent, but to look at it when it's at the full phase, you have to kind of get out there and try it. 16 degrees away from the sun. No excuse not to try daytime observing. All right, that's 32 solar diameters away from the sun. So get out there and try and spot it. And the reason there's a reason for trying to find it in the daytime. It's for practice for later. So next slide, please, Benham. Uranus is still in the evening sky, still near the Pleiades. Transits at about 5 o'clock in the evening. Not far from the Pleiades, relatively easy to find. Next slide, please. So Jupiter is currently the brightest thing in the sky at night, minus 2.4, 41 arc seconds, transiting about 8:30 in the evening. Dave, you saw the last Callisto transit, right? Comments?
Yeah, it was beautiful. You're right. It was very dark. I mean, it almost looked like a shadow eclipse. And also, I got a bonus on that when Io came out from the eclipse itself. I was watching it and I was showing my neighbor and his daughter that.
Oh, nice. Excellent. Excellent. So there's another opportunity coming up on March 17th. Now look at the times. It'll be daylight. All right, so you'll be obliged if you're going to spot this. And I think it'll look really cool in the daylight sky. Jupiter's disk will look fairly washed out, right? Not a lot of contrast in the daytime sky. But Callisto's disk should be even that more evident. So I'm looking forward to trying that. If you practice finding Venus in the daytime, it might be easy to find Jupiter in the daytime. It'll be visible in your finder sky, right? And so you should get out there and try and spot that one. The next opportunity will be on May 6th. Oh, and one other thing, just to go back for 1 second. At the end of this month, Jupiter will be nearing quadrature, 90 degrees away from the sun. And that's where the sky's natural polarization is maxed out. So if you want to improve contrast when a planet or anything is near quadrature, use a single element polarizing filter, stick it in your eyepiece, turn it to, just like your polarized sunglasses, do this, the telescope, the sky, dial out that bright background, and you'll improve the contrast. It helps to see these guys in the daytime. But it's mostly when they're near quadrature. All right, next slide, please.
Does Sal want to show anything at this point? Or?
Oh, do you want to pop your Jupiter picture in?
Yeah, sure. Yeah, I'll just bring it up.
We have a special guest observer's report.
Is that Sal?
There it is.
That's Sal.
Now, can you open that up?
Okay, so this is a picture taken on Tuesday night. Can you expand that? Can you hit that? There you go.
So you're flying towards it.
So I just want to make a point. This is with a 6-inch telescope. So do we consider that a small scope these days?
Reasonably small.
There are some aberrations here, but that's EO, and it has a yellowish thing. And by the way, everything went wrong. This is the first night that I had my scope out because it was in winter hibernation, and I took it out, and everything failed on it. I was actually tracking manually with the hand controller, and that's 30,000 frames. So I had to track for 3 minutes. And I only got two frames, but that's what you can do with a 6-inch telescope. But I've had a lot of help from guys like Doug Paul, John Gaudreau has been holding my hand for years on this whole thing. There's an aberration effect on the right-hand side of the planet, and I think that's from diffraction, but I'm not sure. I think it is. Okay, and there's one more picture in there. I like to.
Sal, what camera is that?
That's a yeah. Why don't you, yeah. So this is my best picture of Jupiter taken 3 years ago. But look at the detail. 6-inch telescope, and I can do anyone in this room can. So Corey was the first guy to show me what to do. Then Doug Paul and John Gaudreau, those 3 guys. So I want to make a point. If you don't know anything about imaging, you have all these experts in this room. They're all willing to help out. Thank you. That's it. Any questions?
If you want any information about visual observing, Glenn and I will. Anyway, Lunar highlight of the month is the lunar X. It will be visible on Wednesday, March 25th at about 6 o'clock p.m. It's visible every month for just a few hours. It's a clear obscure, where for a few hours, the rims of several craters light up in the morning sunlight, and they produce that nice little X. So it's tiny. I mean, where is it? Right there. It's right there.
Do you want to use the
No,
pointer?
it's okay. It's right there. But I do recommend getting out to see it. How many people have seen it before? The lunar X? Yeah, it's kind of cool to see. You just have to know when to look for it. So I'll continue to sort of keep you up to date on that sort of stuff. You can find
lunar V also.
the lunar V is there too. It's
And the Murata M.
It's in. There's a V is right here. That's the V. So cool things to look at on the moon, right? You should get out and look at the moon every chance you can. All right. All right. Next slide. A reminder that in about 2.5 weeks, comet C2026A1 MAPS. It's a Kreutz family sun grazer, and it won't be very visible in our evening skies or morning skies. It's going to just screw by the sun and head right south again. But as a sun grazer, on the afternoon of Saturday, April 4th, this guy here might actually be visible to the naked eye if you get this guy blocked out of your way. If you put this guy behind the wall of the building and be very, very careful, you might actually be able to pick up this comet with the naked eye. It's hard to gauge. First of all, it has to survive passage. It's going to skirt
That's
so
post-perihelion.
close. What's that?
That's post-perihelion.
Post-perihelion, yeah. But it'll pass so close to the surface of the sun that it may just fizzle and go away. Charles, question.
Will it be to the east or the west of the sun?
Well, this has got north up, so to the east. This would be just as you look at it in the sky from the Boston area,
Trailing it.
or from my yard.
Right now, it's to the west,
Got it.
and after it passes perihelion, then it'll presumably be to the east.
It's located right now near the Cetus eridanus border, but it's only about 10th magnitude. It's pretty faint.
It's about 15 to 20 degrees behind the sun.
Yeah, well, the images can,
Again, right now.
images will be able to pick it up. I'm hoping to see it naked eye. We'll report back next month.
Lovejoy did essentially the same thing.
Yeah.
That put on a good show, so we'll see.
Ikea Seiki in 1965 was a sun grazer, a great sun grazer. They put on a great show. So, fingers crossed. Anyway, that's just a little reminder. I'll send out more reminders later. All right, next slide. Glenn, I'm going to make you talk about the next slide. Go ahead, Glenn, you're still with us, right?
Yeah,
Glenn?
I had to, you'll need to unmute yourself.
Can you hear me?
Yeah?
we are.
Okay. Yeah, the double star for the month is K-pop. By the way, I just got on Zoom. I was having a hard time getting. All of a sudden, I see the business meetings happening first, so kind of caught me by surprise. But yeah, it's called K-Puppis. It's one of the most beautiful double stars in the sky. If you like, especially the twin pairs like Gamma Ariatus, it almost looked like car headlights out in space or a cat's eyes or something. Magnitudes are shown right there, 4.4, 4.6. And I went to the Washington double star catalog just to get an update. And the most recent measurements they had were that separation of 9.9. And that's about the same as it was way back around 1800 when it was first observed and recorded. Both stars are B-type stars, so they'll appear kind of whitish in the view. And as it shows right there, it's not that far from the lower part of Canis Major, so we could get a good view from the clubhouse. We have that open area to the south. So next time maybe there's a star gathering or a big session at the clubhouse, check it out. Okay, we go to the next slide.
I know this is a little far south, but it's really well worth it. I called Glenn one night telling him I discovered a nice double star. He'd already seen it. Well, I didn't know he discovered it, but I happened to pawn it by accident. I was so taken by it that I felt compelled to call him. So I wanted to just put this up as a reminder. It hasn't done it yet.
Yeah, I say again, with all the problems we're having with light pollution and the sky is just kind of diminishing, double stars are still there. That star will shine through a lot of of murk that faint galaxies and things like that wouldn't. So it's definitely worth a sight.
And I didn't make that name up. That's kind of the Blaze star. A period of, we think about 80 years. Last eruption was in 1946. So here we are 80 years later. Let's see if it'll happen this year. All right, next slide. And so another opportunity to watch a minima of Algol. This is one of Glenn's favorite stars. An eclipsing variable star, very regular period. So you could predict this thing out years in advance. But on Monday, March 16th, it's coming up next Monday night, at about 8:45, the star will reach a minimum. And so yeah, check it out. If you happen to be out, it's clear. Go out and check it out. It's a fun double star to look at. All right, next slide. I think we're going to the deep sky stuff now. Go ahead, Glenn, you do this stuff.
All right, the one for last month was Messier 1, the Crab Nebula. It's about a 9th magnitude object, kind of small in size, something like 7 by 5 arc minutes. So you got to look for it. The thing about it is, all you have to do if you're a star hopper is just go to Zeta Tauri and literally use a wide field eyepiece and just kind of scout around. You'll start just kind of circle around Zeta, and you'll pick it up. Again, it's about 9th magnitude. You can see it with small telescopes. And we have a couple of images. If we can go to the next few slides. We didn't get a lot of observations. Go ahead, we can go to the next slide. And that's Doug Paul's image. And the thing is, we didn't get a lot of observations, and I blame it on the winter. We started in December and so forth with those bitterly cold nights. It was either a bitterly cold night or it was overcast. Then we went right to the snow, and it kind of shut me down because I'm getting too old to shovel out that observing spot in my backyard. So I've kind of let this winter just go by. And so I haven't done much observing myself. But that's Doug. And you know, since there's only a few people, Doug, give them the specs on your observation, your image.
That's 6-inch, 6-inch refractor. But that's what, 2 hours of data. And if you cheat and use a go-to, you just click in the right place and it's automatically in your field of view.
Okay.
And
this is Mario's image.
Do you folks use go-to mounts? Yeah. Anybody? I've got one. I've just started to play with it. It's pretty nice, actually, when it works. When you've got a polar line. Actually, pretty cool.
When did they come up with that invention?
I don't know. It's new to me. I'm a star hopper.
Welcome to the 21st century.
Welcome to the dark side.
No, I haven't hooked the camera up to it yet. Calm down.
Next year we'll have a cell phone is all over.
I don't know.
Okay, is Mario there?
No.
We have Mario's particulars.
That's
It's still
I don't think
too
he's
cold.
here, but I like being both the images. I like the filaments that you can see. Of course, we've all seen that object. To the naked eye, it looks like just an oval, fuzzy, faint patch of light. But the images can pull out some pretty cool stuff. And here's one of Glenn's.
A quickie comment on comparison. Mine is shot in natural color. Mario's there is done in false color, probably the Hubble palette.
Yep. Okay. Cool.
Okay, and just some final comments. This is my sketch, and again, this was made years ago. I have not been going out and observing so far this winter, but this was made, I believe, with a 3-inch f6 telescope. So again, you can see it with a small aperture instrument, but you'll notice in the image, there's Zeta Tauri up in the other part of the image there with a crab nebula just below it. So they will fit into about a 2-degree field. Now we'll go to the next slide. I think we're going to talk about this month's challenge. And again, we had very few observations last month. It's been a terrible winter, but I really encourage those of you who haven't been doing observations to check this one out. The problem is, if you're a star hopper, this is in no man's land. It's in a barren area of the sky called Camelopardus, or Camelopardus. And this finder chart right here shows one way of star hopping from the stars in the Big Dipper. It's about a 9th magnitude galaxy. I think it's something like 21 arc minutes by 12 arc minutes, but In my scope, all I could see was just that bright nucleus. You're seeing the image right there. And that's only about maybe about the size of the Crab Nebula telling through, just a couple of arc minutes across. But it's a beautiful spiral galaxy. So if you've never seen it, most of your images have go-to instances. You don't have to worry about star hopping. But I'd like to see a whole bunch of images of this particular object because it's a really pretty sight. And finally, we have the one coming up. Here's our preview for next month.
Yeah, I think this is Mario's picture
Whoa.
from 2403.
Yeah, Mario got ahead of the game. He sent one early there, so that's his image of that galaxy. And you can see it's a beautiful spiral. I think it's part of the M81 group. It's associated with the galaxy M81. So it's about 11 million light years away. And finally, coming up, Macarian's chain, basically, Messier 84 to 86 and 7 other galaxies. And I know that finder chart doesn't show it that well, but it's between the nebula, the beta star in Leo, and Venematrix, I think you pronounce it, the Epsilon star in Virgo. And a lot of people star hop from that star to get to the Virgo cluster, but I don't know if you can see it in the image, but there's a star called Rho Virgo. If you look at the circle with the galaxy, it's a little bit to the lower left there. And the thing about that star is it's actually a little part of an asterism shaped like an arrowhead, with that star being in the middle of the arrowhead. And right away, you get the orientation and the field size. It gives you an idea. When you go to Venematrix, however you pronounce that star, you just see the single star. But if you go to Rho, you've got an orientation right away. You've got 3 stars around it, points kind of toward that area. But that'll be the one for coming up next month. That'll be, again, another one for astro images. And
Glenn, what's the approximate field of that red circle? How many degrees?
God, I'm going to guess, I'd say probably at least 5 degrees or more. It looks pretty big. I'm just looking at the chart there, because I can barely see. I think we're...
Circle up just to highlight it. I didn't measure it, but, you know, everybody has their own way of getting from one place to another. When I go into the Virgo cluster, it's pretty, look, it's daunting, right? You've got all these galaxies, and if you've got some aperture behind you, where am I, right? What am I looking at? I always like to start at this T-shaped asterism right here. See that right there?
So people can see.
So I go from Denebola to this T-shaped asterism. And if I'm doing a Messier marathon, I want to come into this part of the sky, I always find this T. I go 98, 99, 100. Don't forget 85 is up here. And then I come back down in here, and then I get over to the chain and all the Messier objects that are down in here. Don't forget M49 down here. Down there. And where's M61? M61 is further south. Never mind. But if you've got some aperture, this chain of galaxies is a pretty cool thing to look at. Roger Iris has got a blog entry that talks about seeing 9 galaxies in the same field of view if you have a low power wide field like this. And some dark skies. There are like 9 galaxies.
I think that's about a 3 degree or so field of view vertically on that.
This one here.
Shot.
Yeah.
No,
this one here. About 3 degrees. Yeah. It's a pretty sprawling sort of thing. You got to kind of star up to it, but you can go right up the chain and look at all kinds of cool galaxies. Pretty neat. So I hope you get out and actually take a look at those. And I think that, Glenn, I think that's it for the observers report. Yes?
Yeah, I'm just going to close. I'm just going to close. I would rather be there in person. I was kind of worried about the roads icing up tonight, which is why I stayed home. But a quick shout out to my friend Sal Arisha. I know you're in the audience there. We had a nice chat today. So as I say always, keep looking up. We'll see you next month.
Glenn, thank you. There are a couple more slides in the observers challenge. In the observers report, oh, I've got the clicker now, don't I? It's the arrow key, right? Yeah. Here, you do it. I always jump about 18 slides ahead. So if you want to take a look at any of these objects, any of the stuff, it's on wood. Did I break it? Nice.
Might need to click it.
So the clubhouse will be open for observing this weekend, although I'm pretty sure tomorrow night's going to be clouded out. There's more hope for Saturday night. March 20th and 21st would be a perfect weekend. That's the new moon weekend. It's a perfect weekend to get yourself going on a Messier marathon. And then April 10th and 11th. Now that is April 10th and 11th. I think that's the NEAF weekend. So a lot of folks might be away. And then April 17th and 18th. And so come on out and hang out at the clubhouse. It's pretty cool. We got lots of cool things to look through up there. So Well, come on out and join us. All right, next slide now.
So I asked John to send me the details of the summary of the work, what he's going to talk about, and about himself. He just gave me just 2 lines of himself. I know he's going to give you a lot of details about the work he's doing, the electromagnetic vector sensor, ionospheric sounder. So he'll talk about that. But so as far as John goes, I dug up a little bit more of his background. So I hope I'm correct in this. So John Swoboda is a research scientist in the Atmospheric and Geospace Sciences group at MIT Haystack Observatory, where he specializes in creating and improving sensors and remote sensing technologies to study the ionosphere and near-Earth space. He holds BS and MS degrees in electrical engineering from Rensselaer Polytechnic Institute and PhD in electrical engineering from Boston University, with a background that combines signal processing, imaging, and radar systems from both academic and industrial settings. Before joining Haystack, Swoboda John worked at MITRE and held research roles in Boston University, giving him experience across government, academic, and R&D environments. At Haystack, his research centers on radar signal processing and instrumentation for monitoring space weather, ionospheric dynamics, including the development of new radar technologies and remote sensing strategies for observing near-Earth space phenomena. He currently serves as a Geospace Research Scientist at MIT Haystack Observatory and is the primary investigator for projects such as EMVSIS, is that how they are pronouncing it?
Emphasis.
Emphasis, leveraging his cross-cutting experience in signal processing, radar engineering, and space physics-oriented sensing to tackle challenging technical problems in space weather monitoring. So here you go. So John, all yours. And,
Yeah, no, thanks for having me. I am, we're all looking at the electromagnetic spectrum here, right? I'm just looking at different parts of it. I'm looking in the HF, UHF, all these places. You guys, much smaller wavelengths, you guys are using glass. We use metal and we use glass too. There's glass in there, don't worry. So I'm my area of expertise. I like to tell everyone my simple way of explaining what I do is I turn electromagnetic waves into scientific measurements. And I like the way that works, nice and quick. And so what we're going to talk about here today is I'm trying to take so if you guys at the ATMoB site at Haystack, right next to it, you see all those 3 towers. The 3 towers are what's called the Digisom. That's an ionospheric sounder, and that's actually looking at the ionosphere and measurements of the ionosphere. You have those 3 towers, and then behind there's a whole field that you have all these antennas distributed out there. That's how that thing works. I'm trying to turn this into 2 antennas that are about the size of a person, and that's it. So we're trying to shrink things down. We're taking advantage of new technology, new signal processing, new and some new antenna technology, signal processing, and just kind of distributed systems. I'm also working with my colleague Brian Bowles, we're sort of doing a double radar. He's got a radar system that's looking at the mesospheric winds. So and it's called a meteor wind radar called Zephyr. Ryan has much better names for his systems. Zephyr is way better than my acronyms. He also has one called Simone. It's so much better. He is so much better at naming systems. But before I get into my ionosonde, I want to talk about quickly the small radio telescope. And today something just happened. So I would say everyone here is a bit of a gearhead. I take it, right? So this popped up where you now might be able to make a little radio telescope for about $1,000. And I have software that does this. I currently run the Small Radio Telescope project at Haystack. If you've ever seen it, it's actually using old C-band antennas. Alan Rogers, who's still up there, if you are familiar with Alan, he has gone to the ATMoB building and put ferrites everywhere at some point or another. That may be me soon, I will see. Yeah, this is like a small dish where you can actually, use the hydrogen line. So I'm gonna be playing, I reflexively bought one of these for myself. We'll see how my wife feels about that, yeah, but that might be one of my little projects I'm gonna try to do, but combine our small radio telescope software with these, low cost, dishes and the discovery drive. And so the drive is able to move the antenna itself. And, maybe at some point we can try to, take some optical, take some radio, and take some things together and see what we see. And that could be a fun little outreach thing at some point. So if anyone's interested, maybe at some point, just walk into Haystack, ask the front desk person, John, where's John? And then I'm probably in my Messman office with all this radio equipment everywhere, and we'll talk about this. So anyway, all right. So what are we doing? So we're looking at. Okay, this is just kind of a nice little we're looking at our atmosphere. So coming back from out in space, far away, we're looking at things now. What's going on in our near Earth space environment? And my area is. I'm looking at the ionosphere, so right here, between about 100 kilometers and 1,000. There's all kinds of cool stuff happening up there. You have aurora, you have meteors burning up, and you have, essentially a plasma out there. One way I like to describe plasma physics and why it's so complicated is if you look at just like fluid mechanics, right? Fluid mechanics has Navier-Stokes. There's like this $1 million prize to figure out basic mathematical aspects of Navier-Stokes. That's just fluids. Now let's take that impossible problem and then add electromagnetics to it and just go hog wild. So plasma physics is tough. That's why we're having trouble with fusion. It's tough because once you start, there's a lot of nonlinearity. The math is more complicated than we would ever than humans really know at the moment. So there's a lot going on. This is hard to measure for us. We have to do. We either have to have very large aperture and high power radars, like the ones at Millstone Hill. Or we're using LiDARs. LiDARs are also you guys know LiDARs are very, very delicate instruments. Very hard you get measurements consistently, but when you get them, they're great. We don't live up there. We can't send someone up there. I'm sure there's a number of people who'd like to send up there, but and then you can fill that in. But we can kind of see you can't get in situ measurements well, so we're kind of doing remote measurements. And so this is where we get to things, we have to start thinking about things like radar. So when we start talking about radar, radar is sending up a pulse of electromagnetic radiation, bounces off, and comes back. There's a number of different types of radars, and what I was talking about here is multi-static radar. So multi-static radar is where you have the transmitters and receivers separate. When you're dealing with monostatic radar, that's the more traditional radar systems, the stuff you see in say car radars. That's where the transmitter and receiver are in the same spot. And now we're dealing with what's called MIMO, so multiple input, multiple output. There's also single input, multiple output, where you have one transmitter bounces off something, comes back to the receiver. You have multiple transmitters for MISO, like the soup, I guess. And it's not just soup. But it bounce off and then you go to the receiver. But with the MIMO, you have multiple receivers, multiple transmitters, and you can almost make a cell phone sort of layout here. And so, our dream is obviously, put all these across the US and measure the ionosphere everywhere and make a three-dimensional map, and that'd be neat. But, what we're trying to do is just show the technology. And, we're kind of able to really get, combinatorial level of, looks at something. Meteors are kind of a classic thing. It's nice to see if you're trying to bounce off a meteor. But with the ionosphere, you're bouncing off this sort of, amorphous blob. And that's what we're trying to do. We're trying to get a nice picture of this amorphous blob and maybe move to not just like a space weather sort of forecasting system, not just So when I talk about space weather, I'm talking about, basically when we start getting the ionosphere and above. So, and, soon we'll have, weather people going, oh, look at this ionosphere here. We're gonna get all kinds of weird stuff, space weather person. Still, the polar vortex will play a role actually, because we're actually doing research on how that does work. Okay, so when we're talking about ionospheric sounding, what we're doing is we're actually just sending up a wave, and it's bouncing off of the ionosphere, and it's bouncing off at its plasma frequency. And what you end up getting is something like a virtual height. And you're getting sort of as you send up as you transmit a set of different frequencies. So you start with, say, for our Earth's ionosphere around 2 megahertz, then you start transmitting higher and higher frequencies, around like 10 megahertz or so, 12 megahertz. And then you start seeing, and what you're doing is you're just measuring the time it takes for that pulse to go from the ground, bounce off the ionosphere, come back to you. That the frequency that it bounces off, that you can then, you can then figure out the plasma frequency. That's the plasma frequency that bounces. The plasma frequency, you can get the electron density from that. So when you get that, you actually can figure out at what height, what electron density is there. And so you're getting an electron density measurement. That's sort of the, how much plasma is there at the moment. These are bigger systems. They've traditionally been bigger systems. Actually, ionospheric sounding was one of the first types of radar that was ever developed. And the layer that, one of the things Marconi first did when he was bouncing electromagnetic waves off, he found the E layer. So we actually have multiple layers of the ionosphere. We call it the E layer because that was the first thing Marconi said. And then the layer above that, F. And then we moved to F. And the one below the E layer is the D layer ionosphere. And then for the F, you want to guess what's after the F layer? G. No, not too big actually. Yeah, they messed that up. So there's a bunch of goofy stuff like that. Yeah, so we go to F2 there.
F sharp.
Oh, they weren't that musically inclined. So you have this sort of thing, it's bouncing off, and they're usually large, and in order to do anything like phasing of anything together, when you're doing, we use a term when we want to get angle of arrival information. If we want to get angle of arrival information, we actually, for us, radio nerds, I'm just gonna talk about how I'm a radio nerd, whatever. But you have to have it has to be your antennas has to be spaced at least 1/2 wavelength away. So when you're dealing with HF, these are really, really large wavelengths, and so then you're spacing things out across essentially, this is this is the Westford antenna right here. Here's the millstone. Here's that little millstone warehouse. The ATMoB's just cut off right here. And then you have all these big towers. And then you have these, in these fields, so in this field around here, you have a bunch of receiver systems that the Digiton receives and signals on. So it's across essentially a huge amount of land, these massive towers. And so, basically we were, I was looking for, we were kind of sitting there at night, talking with a bunch of people at Haystack, and it's just like, well, we can do this. If you combine a couple of things, you can do this much smaller, cheaper, faster, and get more stuff faster. So we, I was talking to my colleague, and he was saying, what if you code the waveforms, use multiple transmitters, multiple receivers, and you use these vector sensors. So a vector sensor, it's right there. So a vector sensor, so we all know electromagnetic waves have 6 components, 3 E's, 3 B's. So E, X, Y, and Z, B, X, Y, and Z. So electromagnetic waves have 3 components. So we always think about this in 3 components, in the 6 components, sorry. So you have 6 components here. So when you have an antenna, you're generally only measuring one part of that electromagnetic field. So you have a dipole. Dipole is like, 2 wires. That's going to measure one component, either the EX, EY, or EZ, depending how you orient that, right? So loop antennas, loop antennas also are there, but they're magnetic. They actually are sensitive to the magnetic field because that induces a current in the loop. That loop current then gets measured by some circuitry, and then you get a measurement of the electromagnetic field of just that one part of the magnetic field. Now, a few years ago, people were like, what if you just made 6 loops and 6 dipoles and monopoles and put them together in a phase center? And yeah, that's basically what this is. This is a vector sensor, an electromagnetic vector sensor antenna. Now, there's actually also acoustic vector sensors, and it's looking at just how, it's actually looking at the velocity of the air. So you have the pressure wave and then the velocity of the air. It's actually a really interesting thing. If you look at vector sensors, well, first off, make sure you're on Harvard's Wi-Fi so you get IEEE stuff. Because that's what a lot of it is. Then you can do things like, so the idea though with this vector sensor is, if you think about, say, the pointing vector, like the pointing flux, right? Where you cross E and B together, that gives you the direction that the wave is moving. It's the same idea. So you can get angle of arrival information just by getting this information. And then you also get polarization. Polarization is very important because if you're going through a refractive medium like the ionosphere, it affects the polarization. It starts moving, like if you have, say, the electromagnetic wave as it goes, it starts twisting in different ways. And from that twist, you can actually extract that information of the medium. So this is the total concept. And so we wanted also to we thought, oh, well, what if we made dual polarization too? So as you send out 2 different polarizations, you actually can track how things are moving through the ionosphere at all kinds of different ways. So we have these are our loop antennas. So we used loop antennas. And this is the reason we use loop antennas for this is actually because of size. These are about 5 feet in diameter, but if you wanted dipoles, it would be on the same. If you wanted something like a dipole, it would be 10, 20, it would be 28 feet. It'd be a huge amount of space. So very compact system design. This is like the size of, you can kind of, these are about, altogether, this is probably about 9 feet high up here at the top, but still comparatively to 100 feet, we're doing pretty well. So you have these dual loops, and one of the things with loop antennas is that you can tune them and get a lot of power out of them if you're able to change the circuit parameters of the loops. I'm going to talk more about that. That's been the bane of my existence for a while now. There's some mechanical components in there that that'll do it to you. So this is kind of our overall idea behind it. We're starting, this comes down to, let's look at and why we came here. Here's our requirements. Our TX, we're trying to keep the power low. Low power is another thing that helps a lot with licensing. So FCC licensing, it is the one way we keep, the skies dark in our bands, but it doesn't always work that way. Well, we can talk about Starlink too. There will be a paper coming out in IEEE DISPAN about our results and what we're seeing in the various parts of the radio band with Starlink too. So that'll be fun, and we're having a number of people talk about various types of I don't know how you deal with all the press for that. Unfortunately, someone's going to be complaining about it, and then we have to deal with that probably. But anyway, but again, this is a situation where we're looking at our transmitters and receivers, and we're trying to get as low resolution as possible, something on 1 to 5 kilometers up 100 kilometers away, 100 to 300 kilometers away. So we're trying to get really high resolution, and you want to keep our power levels low. We can put out about 100 watts ERP, but generally we're putting out something like 10 watts, much lower than that. We have that ERP mainly so we stay within the bounds of our FCC licenses. So I want to avoid, but again, this is mostly in the ham bands, and the ham bands, it's a bit of the Wild West out there. If you're a ham radio person, any ham radio people? Yeah, so you're So you're probably gonna see me in a lot more of me soon. I'll give you the waveform and you can correlate it if you want. Yeah. Anyone going to HAMSI this weekend? No, it's in Connecticut. Okay. HAMSI is a ham radio science conference. It's actually a group where you can do science with ham radio stuff. Our director at Haystack is a big ham radio person and loves ham radio. Exactly. Wonder how he got that. So yeah, this is kind of the nicer splash slide of this. You know, we're looking at all the different how polarization comes into the mix. This is the O mode and X mode. O mode is the ordinary mode. The X mode is the extraordinary mode. I know the name is terrible. And basically what happens is that, you know, your sort of polarization of the wave goes through and starts to twist as it goes through the ionosphere. So that's what the X mode is there. So, and we're trying to get as fast time resolution as possible. That is dependent on, you know, again, our bandwidth. That's dependent on, you know, how many, you know, how many pulses we put out. So this is a bit, and I wanted to say something about this concept. It's actually much different than the digisons. It's actually using a completely different like radar methodology behind it. If you're into that sort of stuff, yeah, talk to me. But yeah, so this is what our prototype system looks like. So we started with the receive system up on top. This is so those are commercial off-the-shelf EDIS radios. Those are software-defined radios. Then we have a bunch of HF, those are some filters, and then you have an octa clock below that. So when we're dealing with, with radio, you're really into time. So octa clocks, we're actually using GPS discipline oscillators to keep everything, we know the time everything's going out. And then on top of that, what we did is we have another just transmitter. We have a little radio transmitter, and then there's like a mini circuits amplifier. And this is a tunable loop antenna. This is our original loop antenna that we had, and it's much smaller. You couldn't really get the bands that you wanted, and also one of the things with ham radio equipment. Look, ham radio people are great. They're doing all kinds of cool stuff, but they love knobs, and I want to put this somewhere where I don't want to have to be there, like Antarctica or like, you know, so we actually talked to the company here and they built us some other antennas that are computer controlled and stuff like that. So it's a different way of doing things. So yeah, we're working on that. I'm still working on, you know, that's kind of one of the things we're doing. Their EDIS radios are commercial off-the-shelf radios we use, and then this is that's a little tuner box again with the knobs. So yeah, when we did the local deployment, I'm just transmitting one frequency. For our case is like what I've been doing a lot of is doing one track. So I transmit a signal. The start, you know, starts at the times at the x-axis, frequency is at the y, and then, you know, just kind of looking at it, I then can turn that into a detection. So I'm looking at vertical range, this is how high up it goes, and I'm seeing the return from the ionosphere coming back. So that's what that little dot is. And the other thing here is Doppler. I'm able to speed too, so I'm able to actually figure out how fast the ionosphere layer is moving up and down. So that's the other thing I'm pulling here. So I'm getting position, I'm getting velocity. That's one of the powerful things about radar is that if you do it right, you get velocity all the time. So you know where you're going, you can track stuff. That's why military loves radars so much, because they can track stuff. And also, like, there's really cool stuff now. If you look up Terradar, they're making a car radar at 300 gigahertz, and you're able to like image like stuff. That's 3-dimensional images. It's really cool. The guy was up at Richard, guy who is our radar nerd king, I like to say. He came up and showed it to us this week, and so yeah. And this is because I'm also this design. This is kind of developed from another colleague of mine, Juha Virinen, but I really like it because I came out of the hard target radar world versus the volumetric target. Again, this is nerd stuff. This is shop talk of my little nerd corner. So yeah, so we decided, okay, those are the prototype systems. We're building out a much larger system with, so for one that we can use consistently. So again, here's the loop antennas. The loop antennas here, and in these boxes are giant capacitors. So you need to have these giant capacitors because you need vacuum variable capacitors, because loops, one of the things about loop antennas, voltages get really high. When you get really high voltages, you need to get vacuum variable capacitors. And so here, right here, you have a belt that is turning this. And this is like a Raspberry Pi and a stepper motor. You know, the company, they did their best, but yeah, they did not do a good job on this belt right here. It's been driving me nuts. And how many of you have dealt with really bad stepper motors and belts? Anything? Yeah, you're all like, yeah, I've been there, man. Yeah, so it's working. So the problem is, like, if the belt doesn't move right, those antennas don't tune, and I don't put out the energy that I want out into the ionosphere. I have less energy, I'm less likely to get a return, and I'm less able to measure things. So it's been tough, but yeah, we've been getting it. We had a company, a radio company, that made amplifiers for us, so we built these all out, and so then we integrate everything in there into essentially something that's a small, like a small chest freezer, and that's all of our radio equipment, our radios, our computers. It's all controlled by a phone system, by cell phones. And so, yeah, this is a really cool thing. So this is all of our assembly for this. The receiver side, we're using, okay, this is getting, again, more in the shop talk, into my shop, where we're dealing with a RFSoC, radio frequency system on a chip. And this thing is it's a big hulking board. This black part in the middle is an FPGA. How many of you know what an FPGA is? All right, so you know the hell that I'm in, because I'm programming that stupid thing. And so I'm using the Casper framework again. That's something that astronomers built, for radio astronomers built. It's interesting. But yeah, we have this going from 100 gig. We actually put in 100 gig. We took NVIDIA Jetsons, and we actually put in a 100 gig card in these. And funny thing is, after that, we learned how hot they got, because it kept shutting down, and we had to put fans in there. So we had to cut holes in this thing, put fans in along top of that. So that was fun. But eventually we got everything kind of integrated together. The radio, this whole radio thing here lives in a box that's like that's got all the RF inputs right here. So that's our receiver side. So the receiver has to be very RF quiet. In the HF band where this thing is at, again, the ham radio people, HF is noisy. It is the Wild West, and it is, I don't know. I was going to make some joke about, like, fastest shot in the West, but I don't know how I'm going to do that. But you can basically, what we do is we're going to put everything as much as we can in metal for the receiver, and then have that off from the transmitter. The other thing too is we have to be very careful about things like power lines. Power lines are incredibly noisy in the HF band. Other random things are just like wall warts that you have are noisy in HF bands. So these are things we deal with all the time. This is probably why I'll be in ATMoB putting ferrites around everything at some point. So sorry. This is what it looks like when we integrate everything together. We have our own custom interface board here. We put in a new fan and heat sink because, again, these things get really hot. So this is the RFSoC, the board. Here's our NVIDIA Jetson precariously sitting there. We like to live dangerously, I guess. But yeah, so we built as much of these as we can. Our main goal was for the 2024 eclipse. So we got most of this together, but right now we're actually like pulling things back and trying to update everything and get some betterment. We want to get really regular measurements and have a distributed network of these receivers. And this will work with our, not just the EMVSIS radar, but the much better named Zephyr meteor wind radar, which Zephyr is the goddess of the wind. I think Greek goddess of the wind. So yeah, much nicer name. And so that's so we're going to be having these combined together. But what's really cool about that is that the meteor wind radar looks at different areas, so they're able to get neutral atmosphere conditions. So that's getting the wind around between about 70 kilometers to 120 kilometers. I'm looking something like, 90 kilometers to like 300 kilometers. So we're having this overlap. So we can start to see like, hey, how are these two systems interacting? And that's where we're really interested in like the science level, like the system science. So when we do site surveys, so again, you guys have, where are the lights everywhere? We have, where are the power lines? And so we took out we have a bunch of little, like RFI surveying devices. And eventually we built this out into a more complicated, there's another system now that we've developed called the Mobile Experiment Platform. It's in a gun case, and it's a radio, another Jetson, and all the tuners you could think of. And yes, it's very difficult to buy gun cases through colleges. They don't like that. Well, it is a Pelican case since, anonymized, yeah. But so here we're kind of we were taking this out and looking at, what's the RFI situation in various places. And we just wanted to understand, like, okay, what are we going to deal with when we put our receivers out? Are we going to have too much noise? Are we going to not be able to see anything? Like, are we going to have it be swamped out? So we did this. So we put a low cost SDR in a little Pelican case right there and did some surveys with a little loop antenna. And it's very nice and bucolic and everything like that. I think, was that Martha's Vineyard? I don't know. I know my wife's boss at MGH has a house in Martha's Vineyard, so he likes us, so it's nice. So we did some site surveys, and then so this is all up for the eclipse. And so what we're doing with the eclipse is we want to put as many receivers and transmitters out as we could. So we basically found a bunch of people who were willing to take stuff, and we got as many as we could. And so we're trying to do 8 receivers that are common electromagnetic vector sensor receivers, and so that would work with both the electromagnetic vector sensor ionosphere sounder and the Zephyr meteor wind radar. We had also the Simone meteor wind radar. So Simone is another meteor wind system. It is from the University of Cooling's board. So IAP is their atmospheric physics. Institute of Atmospheric Physics there. And so you had all these receivers. We're trying to get this all nice and set up. So we tried to get as much as we can, but we only could get so many built. And we had to move around our receivers. Our transmitters, we kept them in the same spot. So when you do a FCC license for your transmitters, you have to have it, it has to be in the same spot. Receivers, they can go anywhere because FCC doesn't know they're there.
Is that what you're using drones for?
Oh, drones were something else completely. Drones were trying to do antenna measurements. Yeah, so we wanted to do antenna measurements with drones, so we could, I don't know. We also wanted to look at the beam pattern of our bigger antenna, but the problem with that is with our antenna, if you transmit too high, it'll actually kill the drone. I'm not kidding. This has happened multiple times on the hill. Yeah, so behind ATMoB, there's a little field, and there's a group of Lincoln people who wanted to look at the beam pattern for the L-band radar, and the drones kept falling out of the sky.
Is that considered incidental electronic warfare?
Yes. It was kind of funny because they really did model it. They went and did modeling in like HFSS or something like that, like electromagnetic modeling of the whole thing. Wow, you guys had a lot of fun. Yeah, and then so we put up our system. So here again, we had an updated version of the electromagnetic vector sensor antenna. This is a long wavelength array antenna, but we adapted it for the Simone receiver. And then here are just sort of our, sites right here. This is at UNH. This is on top of a building, science building at University of New Hampshire. And I have to go and, revive that system. That'll be fun. And then, but yeah, in the end, we can get everything into these boxes. You have a power, that's a bunch of batteries right there. We like to do solar panels with the receivers because then that's less noise. Because then it's all DC and you don't, have any of that noise from power lines. So, I was able to get some data, but I had to keep everything, on a single frequency. I wasn't able to do frequency hopping, just we ran out of time. But I'm able to get returns. I can see the returns from, my different sites. This is the original antenna I showed earlier, where it's just that one antenna. These are the dual loop antennas. And when we get the returns back, you can see again, I get the Doppler, I get the range, how far away it is. And so I'm able to get, these different returns and get what's called oblique. So oblique sounding is when, if you're vertical sounding, you're sending a wave up, it's reflecting back and coming back to you directly up. And then oblique is when it's going through the ionosphere. There's actually a lot more complicated physics happening as it goes through. And so now what we're trying to do is we're actually, we're updating our antennas a little bit. We're fixing the internals of these loop antennas right here. We're actually putting out a folded dipole antenna, very similar to like what you would get at ARRL. Our director wanted his own antenna to play with. He got jealous. No, it's actually sort of another way to mess around with this, because then I can possibly do different types of receiving and transmitting, having more antennas, and so I can do different things that maybe I can do different modes, and that's actually really what I want to. That's actually something I'm excited to do, because I'll have sort of a larger antenna and I'll be able to actually do a lot. I'll be able to actually have more bandwidth, so I can do kind of different things, and so there's things to play with. Again, for me, I'm playing with all this. I'm having a great time. So a lot of what I'm doing, these antenna tuning. So I am trying to tune these antennas. And again, this sort of capacitor setup here, figuring out how, as you change the capacitor, how that changes the frequency, where that frequency peak is. So if the top picture is, you have standing wave ratio, and then you have your, estimated rated percentage of power. So I want to get it to close to 100 for the, ERP as I can. And, the frequency that peak is depends on, the turn of the capacitor. So figuring that out, making that work as something that you're constantly able to update in a reasonable way. And so this can change just on basic things, but there's kind of issues with belt slipping and things like that. So dealing with the mechanical part is tough. So mapping the resonant frequency positions is the important part we're trying to get at. Still working on that, but yesterday I was getting sort of a mini ionogram right here. So these are sort of like, again, I'm just comparing this to the Digison, approximately the same time on 311. But, in these lines right here, I have licenses for this. I can actually transmit on these frequencies. So these are the frequencies that I transmit on, and, comparing these to the Digison, I'm actually pretty close. So I've gotten through the issues with the belts. And also, one of our technicians are working on improving these belts by having deeper teeth, better stepper motors, and and kind of some more tensioning. We could have used some more. We needed another rev of mechanical engineering design, but we finally got that, and that's I'm very happy to get that now. So we've got the basic, we're prototyping the basic systems. We're designing testing systems for a larger network, and we got the initial diagrams. We're going to redeploy. I'm redeploying as much as I can, and then we want to just use, now we're at the point now with us in the geospace world, in the ionospheric science world, we're all about fusion from other sensors. So we're trying to, I think there's that talk about it's like a bunch of blind mice looking at the different parts of an elephant. That's what we're kind of doing. And the elephant is the ionosphere. But yeah, so we're looking forward to that, and so we're doing a lot of stuff, and also for anybody, and also for the small radio telescope, and anyone wants to talk more about that, let me know. And we can chat more about maybe combining that with some optical telescopes. I'd be very interested to do that. So thank you for inviting me, and I hope you found this informative and enjoyed it. Thank you.
Questions?
What did you learn about the ionosphere during the eclipse, and how did it differ from non-eclipse ionosphere behavior?
So the eclipse That's like, there's a lot, like, the thing is with the eclipse, we always thought of the eclipse as sort of this impulse response to the system. So you're basically shutting off the ionospheric, ion production in a very small place for a very short time. So it's really like a delta function happening. And for those people who do a lot of systems work, what does that delta function do? Usually you might see wave modes that come out. Now, from what I understand is that there was a big fight after the 2017 eclipse, where the lunar, about shockwaves coming off of the eclipse. It seems like this time we didn't really see those in the total electron content. So I think that was something where people were still kind of fighting over, like, how the different waves, like, traveling ionospheric disturbances come out of that, and where do they come from. So there's still a lot of, like, how do these, what happens to the lake when you throw the pebble in it. And so they're still fighting over this. Again, I'm much more of a sensor person, so I kind of like give them the data and like, you guys fight over this. But then I watch and it's fun. But yeah, I think we're still learning. There's so much aspects to it, and we're still learning a lot of seemingly basic things. So yeah.
Do you know about strain wave gears that might help your belt fire?
Oh God, I've looked at so many different things.
Yeah, actually, yeah, I was gonna ask, so what is that stepper motor moving? Is it turning the whole set of, the two loops, or?
So the stepper motor, inside there's a capacitor. So the capacitor here, the giant capacitor here has sort of like plates here. And as you're moving that's moving the plates in and out.
All right.
So there's a lot of like resistance.
Yeah.
You said it's under vacuum too, so.
It's a vacuum. Yeah.
Got it.
Yeah, so it's tough to move. You have to have a fairly good power stepper motor, but we're close. The ones that we have now, one of the issue is the teeth are very small on these belts. That's for precision, but the problem is that they end up slipping.
I think you want to look at strain wave.
Strain waves.
Yeah.
I honestly think that we will. Our
Motorized, you know where it is.
yeah.
Yeah, you can get one code.
Not a lot of ribbon direct drive, man, it's great.
Oh yeah, the guys who built this for us, they were more electrical engineers than mechanical.
Do you at least have some kind of feedback when you know when you're in the right place? Or?
Yes, so when I transmit, I have a what's called I can do a voltage a standing wave ratio measurement, and so that's how I kind of figure out where I'm at. So when I kind of like, I start to, I put like a very small test tone in, and then I can kind of figure out if you have if the voltage on the thing going out is higher than the voltage coming back, that means you're doing really well. And then there's like a formula you can use to extract that information.
Yeah, and of course, one thing you have to be careful with in connecting that motor to the capacitor is insulation because of the high voltages. So, Bruce, N9JBT here. I was curious what your call sign is.
My call sign?
Yeah.
Well, I'm honestly, I'm not a ham radio person. It's just like, I know, and I know it's, yeah. I know, so I keep meaning to go and do it, but again, I came into this from signal processing, and so
right.
It was completely a weird spot for me. It's completely different. So I will be at ham side though, and I'll be talking to that specific type of mirror.
Yeah, and I was aware of the ham side, but I'm not the right person to go to that. What amateur groups do you work with, if any, and would you like more, assistance from local amateur radio groups?
I think Hamside is the way to go through it, because Phil Erickson, who is the director of Haystack, is very active at Hamside. And so by going through him, he can then, you kind of go through, he is very active at Hamside, and then he would know, like, hey, we would then talk about different things, like, hey, we're putting this out on this band at this time, and here's how you do it. We're not quite ready for kind of like getting a larger audience yet, But there are other things too we're gonna do. So moon bounce parties are another thing we want to do with the MISA antenna, which is our big antenna. And we often do moon bounces and let people come back. We're gonna update possibly some of the trend. We want to update some more of our radio infrastructure so we can start doing maybe moon bounce parties for people. And then we can maybe have we'll transmit something and then we'll just receive, and then maybe decode stuff from different people. That's been an idea we've been trying to do. We're trying to find a way to, again, update some of the internal parts of our system that we can do that and make that like a normal thing to do.
Yeah. What I was thinking more of though was you were limited in your receiver sites because you couldn't build things quickly enough. There are a lot of ham groups that would be happy to build things for you, that kind of thing.
Yeah. We totally would. For us, we're trying to kind of, we want to make sure our systems, we're very kind of like, we want to make sure our systems really work the first time we get it, and then we can open source the build. So we're very like, we want to make sure what we would put out there would work to start. So we're very much into that.
Well, it will only help you if you have a call sign. You've been doing a lot of, so far your experimentation's been fairly local.
Yeah.
You mentioned at dinner and tonight polar vortex. If you could roll out this, if you could deploy it continental wide, is there value in doing that in terms of understanding the wholesale movement of the ionosphere or any connection that might have with meteorology?
Yeah, so there is Geranchenko, who is the current head of the Ionospheric Science Department at Haystack. Her main area that she's been working on for a long time now has been how the ionosphere thermosphere interacts. So a lot of times people believe that any sort of energy is always one way. It's always going from the thermosphere to the ionosphere. She's kind of poking at that and saying like, nah, I can find examples where things in the ionosphere, you can see that moving, the energy is going down. It's a small amount. It's like 90-some-odd% is going thermosphere, ionosphere. But she kind of shows, there's some things going on here. And it is connected. She's shown things like sudden strat warming and how that is connected to polar vortex, how it's connected to the polar vortex sort of being disturbed. So we often run, we actually run the large radar during times with possible sudden stratospheric warming to see how that might affect the polar vortex. And then, if we see, there's some stuff going on here, that means we might have one of the polar vortex dips that we get. And then that's very, and then things are much colder. And, apparently lately, this has been something that people have found lately that, the disturbed nature of the polar vortex is likely a climate change indicator. Because generally it's a climate, before the climate, before things warmed up with all the CO2, the polar vortex stayed fairly stationary. It stayed, kept everything in the poles. But things have been getting disturbed, so the jet stream starts dipping below. So, and that is something that's been connected to climate change.
How precisely do you have to register the receiver antennas, like in terms of orientation for your angle of arrival? Does it not matter much? Or?
Yeah, it does. Like we're probably going to get like 5 degrees or something like that of angular resolution. But to start, we're just starting with like, for just one receiver, it's like a 10 degree some odd, resolution. So right now we're kind of, the other thing too is because I'm transmitting and I know the transmit site, I can then back out what my orientation is.
Kind of self-describing.
Yeah.
Yeah, actually, I'm glad that Chris mentioned that antenna because I had a question. I was wondering if you have any other cool pictures of like the beam response or anything like that of that antenna.
Yeah, not here. I'm gonna be playing. I gotta make some more of those. So yeah, but I will soon.
And are they? So I know a bit about EM fields, but I'm wondering. So when you get your X, Y, and Z electric and magnetic, Does that mean you're able to reconstruct the direction of the wave is impinging completely from that?
Yeah.
And so that also gives you the polarization?
Yes.
Okay.
Yeah. So it gets all the information in there in one. It's, you can build, like, for example, what's called a phased array.
Yeah.
And you can get better, you can get a much better sort of like, angular resolution as it gets bigger and bigger. But we're also doing what's called, there's been some work by Kat Kadanoff at MIT. Well, she was at MIT, now she's at Lincoln, because Lincoln paid for her to go to MIT. And so her PhD thesis was on using vector sensors for astronomy purposes. And the idea is you put out a bunch of them, and can you do interferometry together? So if you go from an interferometry where you have two antennas, you kind of you correlate the everything together. But yeah, that was her area. And so we're sort of, then you can take advantage of where you have multiple receivers, and then you start doing this interferometry and get a much tighter angle of arrival estimation resolution.
When you're thinking about combining radio and visual wavelengths to make images, how are you thinking about the difference in pixel size and number?
So for me, the way I would probably, what I usually like to do is to start with, if we're going to be trying to compare the two, you can kind of compare, like, I would probably take a circle and say what our beam position is. So if you're familiar with how antenna beam patterns look, I would just take, so antennas have kind of an angular resolution that they would have. And so what I would do is you would take, like, let's say you have a picture of a, celestial object, and I would then put on top of the visual field what the antenna is looking at. And what's happening is the antenna is averaging over essentially like a little circle in that picture and saying, like, okay, I'm able to average this much comparatively. So that's how you would sort of combine the two. There's a lot of, and the thing is, when you're looking at electromagnetic waves, you can kind of think of it, if you take a different frequency you're looking at in the radio spectrum, it's like putting a different type of filter on your telescopes, for example. And then you're kind of seeing different things happening. So at the Haystack antenna, the 37-meter antenna in the big radome, they're looking at, like, masers or star-forming regions that, there's some sort of physics happening that's creating an electromagnetic wave in that band. And then you can then see just a different part of the overall wave process. And so it's kind of like, so for example, if I have a small radio telescope, the big thing you get from a small radio telescope is Doppler. You're figuring out how fast everything's going comparatively. So you can look at, like, I think this, this part of the galactic arms is going this direction and this speed, or it's coming toward us or away from us. And you can kind of then look at it and see, like, okay, I'm looking at different parts of the galactic arms and I can see how they're moving comparatively to us. So that's one thing you can kind of do as a help people understand what information you're extracting when you're looking at these different wavelengths.
Could you put up the slide that has the overview of your system that you had fairly early on?
Yeah.
The one that has the details on the antennas and the transmitters.
Yeah, this one.
Next, I'm trying to figure out which one it was. That had the the transmitter names and the antenna manufacturer name and all that one.
Yeah.
Thank you.
Yeah, so I'm mostly using these were commercial off-the-shelf radios, so Edis radios, and then they have the NI, octa clock in there. So that's kind of the main, what we have here. And then precise RF was the antenna.
Yeah, I want to share that with my radio club. In fact, Would you be willing to give this presentation to a ham club as well?
Yeah, I could do it, yeah.
Without a call sign?
Yeah,
Not needed, not needed. One of the things that my amateur group is really into is wireless technology in general, but ham radio adjacent activities. Because that's how we get kids involved in science and technology and engineering and radio in general these days. So anything along this line, I'm not going to go after anybody that doesn't have a call sign just because they do great stuff like this. This is cool.
Yeah, well, thank you. Yeah, no, I do that talk. I can, honestly, are you in the local Massachusetts area or?
Yeah, Natick.
Oh, yeah. So if you've been to the ATMoB site, honestly, if you just walk into Phil Erickson's office as a director and start talking ham radio and science, he would totally, take up all his time.
What was his name again?
Phil Erickson. His call sign is PJE something or other. Again, this is not my, I'm sorry, I never hung out with you guys. You guys are nice.
Great, thank you.
Yeah, no problem.
Just kidding.
Question, so two-parter, if I may. First question is would your research, would your experiments be sensitive to the small transient disturbance in the ionosphere created by a deorbiting satellite? Question number one.
Yeah, that's good. Honestly, if that, I think so. Like, there's all kinds of traveling ionospheric disturbances that are happening because of these things. There's a recent, and then, I think we would also see things that, like, the meteor wind radar system would definitely be seeing things like that as it burns up. In terms of, if you're getting at sort of the chemical composition changes that we're seeing, that was recently like a Nature article that happened. The one I really want to do is our big increment scatter radars, multi-frequency increment scatter radar or Thomson scatter radar. So the big radars, the ones that are right here. So these are our increment scatter radars. This is zenith antenna, and this is the magnetosphere, ionospheric, steerable antenna. But these actually you can. So this technique you can actually, there's a technique you can use if you have multiple frequencies. Now this radar right here, which is owned by Lincoln Laboratory, is a L-band, a different frequency. And what we can do here possibly, and what I've been trying to get funding for, is to use that to extract composition information. And people have done this at ISCAT in Norway. And I would really love it if we could get data out of that system. Again, I work with Lincoln people a lot. Unfortunately, it's very hard to kind of deal with the security aspects of it, even though the data is not classified. So yeah.
And then part two, very quickly, the depressing part, if we find ourselves in a world in 5, 10, 15 years that's surrounded by 40,000, 60,000, 80,000 satellites, presumably a few thousand in deorbit each year. Some people say that will lead to a thin layer of vaporized metal way up high in the atmosphere. Satellites. Would you be able to map that?
We're already mapping the satellites with our infrared scatter radar. We have what's called now the Starlink layer. We're working on this. Yeah, so around 500 kilometers. The zenith antenna, especially, just with the way that, just with the geometry of this works out. So as the satellites go over, we generally can get rid of them with what we're doing, because if you're moving at any appreciable speed, your Doppler offset is going to be much larger than what we're looking at, like the specific ionospheric signature we're looking at. But with the zenith, since they kind of it's like zero Doppler, because again, Doppler is the cross product. And so when we actually have the zenith Starlink layer, we're working on algorithms to try to reduce it. We're likely going to have to work on new beam modes, which is tough with this type of radar because it's using traveling wave tubes, and you have to be very careful about how that works. It's actually really super, but it's something that we do want to do. It's something that's interesting. But if you can use different wave modes or different waveforms to then, you can try to like remove this reflection from the Starlink satellites. Yeah.
We call them Elons.
I keep trying to commit fraud by saying because I look like him, and get all this money and then donate it to science.
Good.
I know I want to, but I go to these banks and start saying horrible things and it doesn't work still. So yeah.
Right, any other questions?
What types of volumes of data are you generating with like say a day of observation or like the solar eclipse?
In the solar eclipse, I had something like 400 gigs of data on my hard drive, and then the long frequency measurements I have, those end up being something on the order of like, so for 15 minutes of data, that was like 300 gigs. Because again, I'm running at 10 megahertz. And I'm doing 10 megahertz across 6 channels, and then that's 60 megahertz of data. And so that's a lot. It just ends up being a lot. And it's gonna get worse because RF is very voluminous. But there's a lot of information. We have to be clever about how you extract it.
Yeah.
There's a large ecosystem of heavily engineered vacuum variable testers with correct drive steppers and encoders, supports the semiconductor fab industry.
Mm-hmm.
Countless products. Are you tracking that?
A little bit. We outsourced a lot of the capacitor and antenna stuff to the company, and that was just to kind of keep ourselves sane. But I've been looking more into that, and I'm kind of
disassembled a bunch of these, and they're very robust.
Oh yeah. There's a huge industry in this, and the industry is like used in fusion research even all over. It's really neat. I've only just started to scratch the surface on this. But what I really love to do is make a board though, with like, again, a capacitor network where you can kind of switch capacitors in and out. And then you base your capacitance off of like a digital board. And it might be kind of large because it's gonna be high voltage, but everything then is relay based or electronic based, and you just what?
No moving parts.
No moving parts. It might be tough though. Again, the voltages make this tough. That's the big thing.
Oh yeah.
So we are coming to the close of the meeting. So our next meeting is April 9th. And so our next meeting is on April 9th. I think some people won't be here because they are in the NEEF. There is a workshop running at that time, NEEF workshops. So I plan to be there. So I'm not sure if I will be here. So Kerry might have to. But if you're here, you're not here?
Oh, I will be attending a workshop. I'll be here.
Oh, okay, great. So most likely I will be going, not sure. What else? Next month's speaker is someone who is going to talk to us on Zoom. He's talking to us from London. Is something about history of some of the original telescopes and the MIMOs. It'll be very interesting. Quite different from what we have been before. So that's it. Thanks very much.